Okay, here we have question 1 on the F325 January 2013 paper. Unusually, this paper starts with a transition metal question, and it looks rather like an F321 question because it's testing your ability to use the periodic table to find the answers for these elements. So the first one, the element has atoms containing 6 electrons in the 3D subshell. So we need to look at the periodic table and remember that our specification only looks at the period 3 D block elements, and the numbers correspond to the number of D electrons. So scandium is 21, it's got 1 D electron. Titanium 22, it's got 2 D electrons. So the element with 60 electrons is iron. Next one, 2 elements that have atoms with 2 unpaired D electrons. So if we go back to F321, when we did electrons in boxes, and we start filling, so these are my 5D orbitals, start putting those D electrons in. First one with 2 unpaired electrons is the element that is 3D2, which would be titanium. And then if we carry on filling that D subshell until we get another 2 unpaired electrons, and there they are. So it's the element that is 3D8, which would be nickel. Next, this links into things that you should have learnt this year. So complexes with chloride ions, there are 2 that you should know. Got CuCl4 2-, which is yellow. And we've got CoCl4 2-, which is blue. So the answer is cobalt because that's the blue one. And then we've got this compound X3O4. So what we're going to do is take away 4 lots of oxygen, which gives us 164.7. That's 3 lots of X, so we do that number divided by 3, which gives us 54.9. And then we go back to that periodic table, so 54.9, you can see it's here, it's manganese. Next question, we're talking about atoms, so we're going to be using Avogadro's constant. So we do 6.02 times 10 to the 23 and multiply that by the mass of one atom, and that will give us the mass of 1 mole, which is 52.0. Again, back to the periodic table, 52 is here, that's chromium. Carrying on with this question, so we've got some ligand substitution reactions going on here. We're starting off with the hexa-aqua copper 2 ion. When we add ammonia to it, these are all complexes that you should have learnt. So we get 4 amine ligands and 2 waters in that dark blue complex, and it retains its 2+ charge because these are of course neutral ligands. This reacting with sodium hydroxide gives us a precipitate of copper hydroxide because that's the precipitation reaction. This one again is a ligand substitution, and we get that yellow complex that we've already mentioned above. There. Perfectly fine to write that like this, or you can put your square brackets around it. Either is acceptable. Carry on to the final part of this question. So we're talking about nickel. State the shape of the complex ion in this. We've got 6 water ligands, therefore it's octahedral. Formula of the complex ion of nickel 2+ containing 6 fluoride ligands. So we've got NiF6, put our square brackets around it. Nickel's 2+, we've got 6 F-, so the overall charge will be 4-. And then we've got to draw some 3D shapes, so nickel with 3 En ligands. We know that that's going to be octahedral. Again, if you're struggling with drawing these bidentate complexes, go and watch the tutorial on drawing bidentate complexes. So the EN ligand bonds with the nitrogens, we put our bridge in, and then we fill the rest in. Okay, so you should be getting well practiced with these by now. I'm just going to pause whilst I put the rest in for you. And there we have the two stereoisomers. So we've got 1 mark for each structure, and that they are mirror images of each other. So nice, quite straightforward transition elements question for question 1 on this paper. Okay, question 2 on this paper is the acids question, and what we've got here is some pH curves. So if we go down to the bullet points, which tell us what we're going to be doing, and it's telling us that we're going to sketch 2, 1,4-HCl, which is strong, with sodium hydroxide, which is also a strong alkali, and then the second one we've got ethanoic acid, which is weak, and still sodium hydroxide, which is strong. So if we deal with these two titration curves, the first one then, strong acid, so we're going to start round about pH 1 to 2. Strong alkali, we're going to finish up at 13 to 14. The end point is going to be at 25, so that vertical section needs to be round about 25. And then you're probably going to be able to draw this much better than me with a ruler, but I'm going to try and do my best on the computer. So you should have, obviously you're going to draw yours with a ruler, and that's the shape that we should get. So starting at 1 to 2, either a slight rise down here, or it can be flat, and then a slight rise here or flat again, but it must be vertical in this central section, and it must be round about 25. Okay, so that's the strong acid, strong alkali one. Then we're going to try and do the same thing for weak acid, strong alkali. So this time we're going to start somewhere around about 3 to 4, but we're still going to finish up at 13 to 14. So let's try that again. Remember, the end point's still going to be somewhere around about 25 because we've got 25 here. So we'll go back to fill those other little bits of this in. Okay, so they are the two curves that I should end up with. And if we look at the marks on this, so we're looking for at least one of these to have that general S shape. So 1 for the shape of either. So if you got one wrong, it wouldn't matter because you'd get the shape mark anyway. We're looking for 1 that the vertical section is at 25. Now there's a little bit of leeway with that, so if it's not exactly on 25 it'll still be okay. So 1 for ends at 25 centimetres cubed, which you can see is up here in the text. And then we've got the pH at the start, so 3 to 4 for the weak acid, 1 to 2 for the strong acid, 1 for that. And we've got the pH at the end, so 13 to 14 on both graphs because they are both sodium hydroxide, which is a strong acid. Sorry, strong alkali. So that's the 4 marks for those titration curves. And then we're talking about how the choice of indicator is linked to the pH curve. So again, this is an easy 1 mark question. You should say that the indicator must change colour in the vertical section of the titration curve. Okay, so you'll remember doing that in class and looking at selecting different indicators. Sometimes you'll get asked to do that on a paper, but this time we're just being asked to explain how we choose the indicator. In part B of this question, we've got another definition. This time it's enthalpy of neutralization. And what we need to say is the enthalpy change when 1 mole of water is formed from the reaction between an acid and an alkali. Okay, very crucial in this definition that you do say 1 mole of water and that you don't say 1 mole here or here. Okay, so if you say formation from 1 mole of an acid and 1 mole of an alkali, then you do not get them out, because if you think about something like sulfuric acid, then if you use 1 mole of sulfuric acid, you're going to get more than 1 mole of water. So it's very crucial that you realise that in this definition. Coming down to this calculation, okay, so we've got an experimental determination of the enthalpy of neutralisation, and we've got, let's just write the equation at the side over here, so we've got HCl reacting with sodium hydroxide to make sodium chloride and water, and then we've got 35 centimetres and 2.4 for the concentration of sodium hydroxide, 35 for the volume and 2.4 for the concentration of HCl. So it really doesn't matter which of these we work out the moles for, so we'll come back to that in a minute. First thing though, we're going to work out Q, and we're going to use MCAT for that. So the mass, remember the mass is the same as the volume of solution, so we've got 35 plus 35, so that's 70, times 4.18, which is in the question, and times by delta T, which is here. And if we do that, then we get an answer of 4827.9 joules, and that's the first mark. Next thing we're going to do is we're going to work out the moles of water. Okay, again if we look back up here, we've got 1 to 1, and that's also 1 to 1 with water. So we work out the moles of anything from the left hand side, we've got the moles of water. So we're going to do concentration times volume, volume times concentration, divided by 1000, and that gives us 0.084 moles. And we get a mark for that. Final step in this calculation is to work out delta H, and we do that by doing Q divided by N. So we've got 4827.9 divided by 0.084, and don't forget that we're going to divide that by 1000 to convert from joules into kilojoules, and the final answer we should get is 57.5. Lastly, we need to realise that the temperature went up, therefore it's exo, and we give it a minus sign, and that's the third mark. Bottom of this question, so we're repeating this experiment. So in that first experiment, in the beaker, we had a total volume of 70 centimetres cubed, and in this second experiment, we've got a total volume of 105 centimetres cubed. Okay, so, however, even though the volumes increase, we've got the same number of moles of HCl, so this is still 0.084 moles. So we're going to have the same amount of energy released. So we're going to say that same amount of energy released, but it is spread over a larger volume. Okay, so if you've got a certain number of kilojoules of energy heating 70 centimetres cubed, you're going to have a bigger temperature rise than that if that same energy heats 105 centimetres cubed. So that's the first mark for this question. And then it says, predict what the temperature rise will be. So if we think about the way that we might do this, because you're going to have to make an estimate of it. The way that I thought about doing this was by working out how much the volume had increased. So if I do 105 divided by 70, then that means that the volume's increased by 1.5 times. So I thought, well, I'll divide the temperature increase, which was 16, by 1.5, because that's going to go down, and that gives me 10.67. So I'm going to get about an 11 degrees rise in temperature. And that's the second mark. Question 3 is about enthalpy and entropy. And we're going to start off with some definitions. Again, 10% roughly on definitions. Can't afford not to learn your definitions. So we've got enthalpy change to solution, one of the very easy ones. So enthalpy change when 1 mole of a compound dissolves. It's that simple for that first one. Next definition, enthalpy of hydration. So this one, enthalpy change when 1 mole of gaseous ions forms 1 mole of aqueous ions. And for this definition there's 2 marks, so we get 1 mark for mentioning 1 mole somewhere in it, and then 1 mark for gaseous ions turning into aqueous ions. So 1 for this definition and 2 for this one. And then we're looking at the difference between the hydration values. So if you remember how to do this, it's crass. So we've got charge, radius, attraction, and size of enthalpy change. Okay, so let's look at how we'd write that. So we'll deal with the charge first of all. So we say that Mg2+, it's very important that you either say the magnesium ion or you put Mg2+. If you just put Mg, then you will not get any marks for this. So Mg2+ has a larger charge than Na+. Again, you've got to have that plus sign in there. That's the first mark. So we've dealt with the charge, then we're going to look at the radius. So Mg2+ has a smaller ionic radius than Na+. And the final one, so we said we were going to talk about attraction. So Mg2+ has a greater attraction towards water molecules. Okay, so if we were following through with this model answer, we'd then say that Mg2+ has a more exothermic enthalpy of hydration. However, we've been told that earlier on up here, so we didn't need to go for that fourth point here. However, it doesn't hurt us to learn it. Other things that we might want to say, or we might be careful about, is if here you were to say atomic radius, then you would lose that mark. So you might even be better leaving the word ionic out, because if you just said Mg2+ has a smaller radius than Na+, you'd have got the mark. Or if you even just said Mg2+ is smaller than Na+. Okay, so if you're going to use the word ionic in there, then make sure it's that and not atomic. Carrying on, we've got a Born-Haber cycle to fill in. This one is the solution one because you can see it's got fewer lines. So we've got, on the top line, we are going to have those ions, and they are going to be gaseous ions. And then when we go down, we hydrate one ion. So let's hydrate this one. And we keep the other one the same. And then that's the cycle completed, so 2 marks for that. And then it says calculate the enthalpy change of magnesium hydroxide. So we're going to need to put some values on these lines. So if we look back over here, we've got hydration of Mg2+ minus 1926. And then we look for the hydroxide ion, that's minus 460. But there are two hydroxide ions, so we're going to times this by 2. So if we write down our calculation, we need solution as well, sorry. So the enthalpy change of solution is minus 152. Let's put that on here as well. Lattice enthalpy is what's missing, that's pointing down, so we're going to go clockwise around this Born-Haber cycle, so we're going to have minus 1926 because we're going with this arrow pointing down. We're going to have 2 times minus 460, and then we're going against this arrow, so we're going to change the sign, so plus 152. And when we do that calculation, we should end up with an answer of minus 2694. So minus 2694, and that's going to be in kilojoules per mole. It's 2 marks for this question, 1 for a correct process and 1 for your correct answer. So if you had forgotten to times this by 2, then you would get 1 mark. Is where entropy comes into this question. We can see in this table we've got S values, so at some point we're probably going to have to do SP, SR. But before we get there, we're going to have to explain these 2 bullet points. Remember, bullet points tell you how to structure an answer. So we've got explain why when water melts or boils delta H is positive. So we'll start with that bullet point. So we say, apologies I don't have a delta sign. So if you think about, we're going from ice to liquid water, or from liquid water to gas to steam, what we need to do is break intermolecular forces. I might go one step further and say this requires energy, just in case. Okay, so we get the mark here for saying that intermolecular forces have to be broken. This is kind of belt and braces, that we're saying it requires energy to break those forces. Second bullet point, we've got when water melts or boils, S increases, so entropy increases because disorder increases. So that's going to be our second mark, and we need to say molecules, let's change that, gases are much more disordered. Okay, so 3 marks, and let's just run through them again. So we've explained why delta H is positive. We've got to put energy in to break those intermolecular forces. If we're going from a solid to a liquid to a gas, then entropy is going to increase because disorder increases. And then we need to make some sort of statement about the fact that gases are the most disordered, but we need to get this idea that they are much more disordered across, because this is in bold on the mark scheme. So you don't have to word it exactly like that, but you must get that idea across. And they're the 3 marks for that question. Then it says, using the data in the table, show that ice melts at 0 degrees. So this is a minimum temperature question. Okay, so if you think about ice melting, the lowest temperature at which that will happen is 0 degrees. Once you get above 0, then of course ice is going to melt, but the minimum temperature that process happens is 0 degrees. So what we're going to say is that delta G equals 0. And just by saying that, we're going to get the first mark. Okay, but now we're going to need to do some calculations. So if we use our delta G calculation, so delta G equals delta H minus T delta S. But we've said that delta G is 0. Now we can rearrange that to give us T equals delta H over delta S. We've got delta H because it's up at the top here, because we've got water melting. So delta H is 6.01. But we're going to need to find delta S because we haven't got delta S, we've got S values in this table. So we're looking at water turning from being solid ice into water liquid. So if we're going to do SP minus SR, we're going to have 70 take away 48. So let's put that down here. So to calculate delta S, we do 70 take away 48, and that gives us 22 joules per Kelvin per mole. Obviously, delta H here is in kilojoules per mole, so we're going to need to convert delta S into the same sort of unit, so into kilojoules. So we're going to have to divide it by 1,000. And that's now in kilojoules per Kelvin per mole. And that can go up into this calculation here, and that gives us a final answer of 273 Kelvin, which is of course 0 degrees Celsius. So we've proved that ice melts at 0 degrees. That was the gist of this question. So we get 1 mark for that calculation of delta S. We've said that we got 1 mark for stating that delta G equals 0. And we get 1 mark for showing this calculation. And that's the end of question 2. Question 4 on this paper is a rates question, and we've got the reaction of I- ions with S2O8, 2- or thiosulfate ions. It's an equation that you should be familiar with from transition metals and those redox titrations. However, this is a rates question, so it's coming up in a different context. Slightly different for a rates question too, because normally you'll be given some rates data and asked to analyse it. This time you've been asked to explain how you would carry out an initial rates experiment. Now you'll have done this experiment in class. It's the thiosulfate cross experiment, and you need to explain what you did. So we're going to change the concentration of I minus whilst keeping the other the same. Okay, so that's the first thing we're going to say, and then we're going to do the opposite. Okay, so that's the series of experiments. When we look at this question, and the first bit here says outline a series of experiments that the student could have carried out. So first thing, we're going to change I minus, keep the other the same, and then we're going to change the concentration of S2O8 2 minus and keep the I minus the same. So they're the first two things that we're going to get. And then it says, how could the results be used to show that the reaction is first order? So the first thing we're going to need to do is calculate a rate. So rate can be calculated using 1 over T, which you would have done in the experiment, or you could say rate equals concentration divided by time, either one of those for the third mark. And then the fourth mark, you need to say that if it's first order, then rate is directly proportional to concentration. Or you could have said that when the concentration doubles, the rate doubles. Or you could have explained that if you drew a rate concentration graph, it would be a straight line passing through 0. But we've got 1 mark for each of these 4 points in this question. Carrying on down to the bottom, we've got a rate constant calculation. So if we look at this, it says first order for I minus and first order over here as well. So we've got rate equals K, and then we put those both in. We want K, so we're going to rearrange this. And then we're going to put the numbers in, so the rate is here, and the concentrations are up here. And when we put that into the calculator, we get an answer of 3.75. If we look at units, we've got moles per decimetre on the top per second, because that's the rate. Got two lots of moles per decimetre on the bottom, so we can cancel one of those, leaving us with moles to the minus 1, because that comes up to the top, dm cubed, and the seconds to the minus 1 stays the same. So our marks, we've got 1 for this rearrangement, 1 for K, and 1 for the units. Part C of this question is about electrode potentials. You can see that we've got 3 half equations, and it's asking us to write 2 equations, one for I minus reacting with Fe2 plus, so that's these 2 half equations. If we look at the potentials, this one's going to go forwards because it's more positive, this one's going to go backwards. Look at the electrons, 2 in this equation, 1 in this, so we're going to multiply the top one by 2, and that's going to give us, when we put it together, 2I minus, because this is going backwards, plus 2Fe3 plus, and that's going to make I2 and 2Fe2 plus. For the second equation, we're going to do these two ions, so that's these 2 equations. This one's going to go forwards, this one's going to go backwards. Again, we're going to multiply this one by 2, and that's going to give us and of course it's 1 mark for each correct equation. And then we've got why the reaction of I minus and S2O8 2 minus is also catalysed by Fe3 plus. So if we look up here, let's just tidy that up. There's the Fe3 plus, and there's the I minus. So Fe3 plus can also react with I minus. So that's all we need to say down here. And that's question 4. Question 5. This is a KC question. It's quite late on in this paper, the KC question. However, we've got methanol being prepared industrially to make carbon monoxide and hydrogen. So we've got some information here in the bullet points. So a chemist mixes together. Okay, so first thing to note, if they're mixing it together, then this is the start of the reaction. So these are the initial amounts. Okay, so this should be pointing you towards doing an icebox or ICQ, whichever way you remember it. So I'm going to write that down over here to start off with. Remember, it's always useful to put the equation at the top just to remind yourself what you're working out. And we might as well put the numbers in. So if they're mixing together 0.114 of carbon monoxide and 0.152 of hydrogen, it's the start of the reaction, so we are going to have no methanol. Okay, then we carry on. Container is pressurized and then sealed, and total volume is 200. Now this will become important when we get to the bottom of this process. It's heated to 500. That's not really important to us because it's just telling us that KC is temperature dependent. and it says the volume is kept at 200. Then at equilibrium they find that the moles of methanol is 0.052. So at equilibrium, that's this row here, we've got 0.052 moles of methanol. Okay, so now I'm going to change the colour of my pen because you can see that the black writing is what I filled in just from the question. And then I'm going to move to this red pen to write out what we're going to work out. So I'm going to work out the change row now. So the amount of methanol has increased by 0.052 because it went from 0 to 0.052. Then we're going to do carbon monoxide. So if methanol is increasing by 0.052, then carbon monoxide is going to decrease by the same amount because we've got a 1-to-1 ratio in the equation. Hydrogen, however, is going to decrease by twice as much because we've got a 2-to-1 ratio. So we're going to do 2 minus 2 times 0.052. So 2 times 0.052 is equal to 0.104. So that's going to go down by 0.104. So that's where this number comes from. Then we need to work out how much we've got at equilibrium. So we started with 0.114 and it decreased by 0.052, leaving us with 0.062 moles of carbon monoxide at equilibrium. Similarly, hydrogen started at 0.152, it decreased by 0.104, leaving us with 0.048 moles at equilibrium. And if we get these two numbers correctly, then that is our first mark. Next we're going to do the equilibrium concentrations line. So remember, if you're doing an ice box, you will need this second E if the number of moles on each side of the equation is not the same. So on the left we've got 3 moles and on the right we've got 1, so we're definitely going to need to do that second line. And that's why this volume is important, because concentrations are in moles per decimeter. So if the volume, think back to the examples that we've done in class, if the volume was 2 decimeters, then on this row we'd be dividing everything by 2. However, in this example the total volume is 200 centimeters cubed, or 0.2 decimeters. So what we're going to need to do on this one is times by 5 to make 200 into 1 decimeter. So if we do 0.062 times 5 we get 0.31. The same to 0.048 we get 0.24. And if we multiply 0.052 by 5 we get 0.26. And the second mark comes for this number here. Okay, so if we're doing ICQ, then the next thing in the process is to do KC. So we do products over reactants. And we get 1 mark for writing out our expression. And then we're going to substitute those numbers in. So 0.26, 0.31 with carbon monoxide, and 0.24 for the hydrogen must be squared. And that gives us an answer of 14.6. That's the 4th mark. And then we've got to do units. So if we look at that KC, again we've got 1 lot of moles per decimeter on the top. We've got 3 on the bottom. So we can cancel 1 lot out. So we've got 2 moles on the bottom, so they turn into moles to the -2 as they come up to the top. 2 lots of dm to the -3, so they become dm6. And we get final mark for the units. Okay, in part B of this question, now this was actually quite tough. So we've got this procedure is repeated using the same amounts of CO and H2, but it's heated to a higher temperature. Okay, so the volume's the same, but the temperature's different. Increased temperature, however, remember you're going to give the particles more kinetic energy. We're going to try and expand. We've got increased pressure. So 2 bullet points that we need to deal with. Why is it difficult to predict how the yield of methanol will change? Remember, yield is related to equilibrium. And then we've got what happens to the value of Kc. So let's just put that equation here so we know what we're dealing with. It's reversible. And we need delta H, which was minus 94. Okay, so them are the bits of information that we need. So now I don't have to keep flicking back and forth. So why is it difficult to predict how the yield of methanol would change? Right, so they're increasing the temperature, so let's deal with that first. Increased temperature shifts equilibrium to the left. Okay, so if you look at this up here, we've got minus 94 kilojoules per mole for the enthalpy change, so that means that in the forwards direction it's endothermic. So we're going to say because we have to explain it, the forwards reaction, so you must state the direction, is exothermic. Okay, and that's our first mark, and we have to say all of that to get this mark. So we've got to say what happens to equilibrium and why. So if it's shifting left, then we might as well deal with Kc as well. So Kc decreases. Remember, Kc is temperature dependent, so if we're talking about temperature, we need to talk about Kc, because forward reaction is exothermic. Okay, so again we need to say what happens and why. Even though we're kind of repeating ourselves, we still need to say it. So Kc decreases because the forward reaction is exothermic. And then we're going to deal with the pressure. So it says that the pressure increases, so we're going to talk about equilibrium. So increased pressure shifts equilibrium to the right, and then we need to explain it again. So because there are fewer moles on the right. Okay, so 1 mole on the right, 3 on the left, increase the pressure, it's going to shift to the right. So 1 mark for that. And then we've got why is it difficult to predict. So we have to say the relative effects of temperature and pressure are unknown. And that's the final mark. Okay, so let's just look at that final statement, because what we said is if we increase the temperature, it's going to try to go to the left. If we increase the pressure, it's going to try to go to the right. So if we're doing both of those things at the same time, then we don't know which of those things is going to have the biggest effect. Is the temperature going to win over the pressure, or the other way around? So is it going to go left or right? We're not sure. And that's what we're saying there. The relative effects of temperature and pressure are unknown. Question 6 is an electropotential question. You can see that we've got a table with 5 half-cell equations in it. Going down to part A, it's asking us to work out how we do the standard electropotential of redox system 1. So this should tell us that we are going to draw the standard hydrogen electrode. And again, we look at the bullet points, because if you've got bullet points, then that's how it wants you to structure your question. So the first one says, draw a diagram showing how the standard electrode potential, so there again we know that we're drawing that hydrogen half cell, could be measured for redox system 1, that's this one. So let's get on with the drawing. This is a diagram that you should know for the hydrogen half cell. Key thing though is that you label it, so we've got hydrogen gas going in at 1 atmosphere. Lots of people forget to label the platinum electrode. And then in solution we've got H plus ions at 1 mole per decimeter. Okay, so first mark for this diagram is for labelling all three of those things. Next, it's talking about comparing to redox system 1. So if we look at redox system 1, we've got iron 2 plus ions in the solution, and we've got an iron electrode. So we can use a solid bar of iron as that electrode on this side. So I'm going to draw that half cell using solid iron as the electrode, and then we're going to label it. And in solution we add Fe2 plus at 1 mole per decimeter. Okay, so second mark for this diagram is for these two things here being correctly labelled. And then the final thing we're going to do is we're going to connect this circuit. So we've got a voltmeter connecting the electrodes and a salt bridge connecting the two solutions. So the third mark, the examiner is going to look that you've got a voltmeter, you've got a labelled salt bridge, and then they're going to follow your circuit round and make sure that you've left no gaps in it. So I've taken care to make sure that all my lines are connected. And that's the third mark for the diagram. And the fourth mark, so second bullet point, state the conditions. So down here we're going to say solutions are 1 mole per decimeter. The temperature is 298 K. And the pressure is 1 atmosphere. And that's the fourth mark. Carrying on down then. So it says when an alkaline hydrogen-oxygen fuel cell is being used to produce electrical energy, chemical changes take place within the cell. Write half equations. Now you might be tempted to start trying to make these yourself and worrying about balancing them, but all you need to do is to go up to this table at the top. Okay, so we're looking for what's happening at the oxygen electrode. Well, these are the two equations with oxygen in, and the question says that you're looking for it in alkaline conditions, so there is the OH minus. So what we're looking at is system 4, and then we're going to do the same thing for the hydrogen. So we've got hydrogen present in numbers 2 and 3, and we're looking for alkaline conditions, so that's here with the OH minus ions, so we're looking at system 2. Okay, all we're going to need to do is copy these down into the question at the bottom, but we do need to look at the oxygen is going forwards because that's positive, and the hydrogen is going backwards, and we're going to need to flip this equation when we write it down. So we're just going to copy those down onto these lines, and that's going to get us the marks. So we've got O2 plus 2 H2O and 4 electrons, making 4 OH minus. So I've just copied that down from the table at the top. And then underneath, because we said that the hydrogen half cell was going backwards, I'm writing this back to front. I've flipped it. And that's two pretty easy marks actually for just copying down two equations. Then it says write the overall equation for the cell reaction. If you'd picked the wrong two and you'd gone for the acid ones, you could still do this second part because you'll still end up with the same equation. If we look though, this first half equation's got 4 electrons and the second's got 2. So we're going to multiply the bottom by 2. And then I'm going to do my rough working down here. So we've got O2 plus 2H2O and 4 electrons from the top half equation. And then for the bottom, 2 H2s because we're multiplying, 4 OH minuses. On the right, top equation gives us 4 OH minus, and the bottom gives us 4 waters and 4 electrons. Then we're going to cancel things, so we get rid of the electrons because there's 4 on both sides. 2 waters over here, so we can get rid of 2 there. 4 OH minuses on that side and 4 on this side. And then I'm going to write the tidy equation on the line, so O2 plus 2H2, that's what we're left with on the left, makes 2 waters, and that's our equation. Carrying on to part 3, it says what is the standard cell potential of this fuel cell, so you should remember that E cell is equal to the positive terminal take the negative terminal. So we'll go back to that table. We've said positive terminal, so it's here, it's plus 0.40. I'm going to take away the negative terminal, which is minus 0.83. And that gives us an answer of 1.23 volts. So we're going to write that in over here. Then we've got one important difference between a fuel cell and a conventional storage cell. Remember, conventional storage cell is basically a battery, I should think of it. And what we say is fuel cells react a fuel with oxygen to make electrical energy. So this links back to some of the other statements you'll have learnt. So you should know that fuel cells require a constant supply of fuel. Think about a conventional battery. You don't need to fill them up with new chemicals. It's all stored within it. But fuel cells need that constant supply because they react the fuel with oxygen to make electricity. Underneath that then, we've got this next question that says, people assume that hydrogen and oxygen fuel cells are carbon neutral. But this is not true, so we do get some carbon dioxide. And the thing that you'll be used to saying is that energy is required to make H2. Okay, so you'll have probably learnt that as one of the disadvantages of fuel cells. However, that doesn't explain the carbon dioxide, which is what this question is asking about. So we need to say this energy is produced by burning fossil fuels, which of course produces carbon dioxide, which is what this question is talking about. So just this first statement's not enough. We need to explain where the carbon dioxide comes from, and of course it comes from burning fossil fuels. Final part of this question. So 4 marks. This is the toughest part of this question, so you might be kind of wanting to stop here, but you need to look at this question. And I'm going to draw a picture because it's always good to have either a kind of drawn or mental picture of what's happening. So it says a half cell is made from a strip of chromium. So there's the chromium in a solution of aqueous chromium 3 sulfate. So we should know that that's got Cr3 plus in it. And the second half cell has got a strip of X in a solution of XSO4. Now this is very, very crucial over here because you should know that SO4 has a 2 minus charge, which means that X is 2 plus. Okay, and then these two things are connected together to make a whole cell. And then we've got some information at the bottom. So the chromium electrode gains 1.456 grams in mass. So here we've got a mass, and we're going to convert that into moles. Okay, so again, if you get to this question, maybe you're short on time, or maybe you kind of get a bit put off by the words in it. If you see a mass, turn it into moles because you'll get the first mark. Now, also very important, talked about this quite a lot, is labelling what you're doing at each step. Okay, so I'm going to take this mass and I'm going to find the moles of chromium. You need to set unstructured answers like this out nice and neatly with labels so that the examiner knows exactly what you're doing. So we take the mass and we divide by the MR of chromium, which is 52, and that gives us 0.028 moles, and that's the first mark. Okay, next thing, we need to work out the moles of X. So for this we're going to need a ratio. So if you think about the things that are reacting, we've got Cr3 plus and X2 minus. Now the common number with these two charges, sorry, I've put them the wrong way around, no I haven't, 2 plus. Common number with these charges is 6, so that means 2 chromiums are going to react with 3 X's. Okay, and if we identify that ratio, then we get the second mark. Now if you don't get this ratio, you can't get any of the remaining marks in this question, so that's why it was so important that you realise that SO4 was 2 minus, which gave us the X2 plus, which gives us the ratio of 2 to 3. So now we're going to work out moles of X, because we're going to use our molar ratio. Don't really need that charge. So if the ratio is 2 to 3, so I'm going to do 0.028 divided by 2 times 3. Or in other words, I'm going to multiply it by 1.5, and that gives me 0.042 moles of X. And that's mark number 3. Final bit, for X I want the MR, because if I need to identify metal X, then I'm going to need to know its MR so that I can go to the periodic table. So I know that N equals 0.042. I know that the mass is 1.021 because that's up here. So I can do MR equals M over N, sub the numbers in, and that gives me an answer of 24.3. That on its own is not enough, because then I need to go to the periodic table and say that 24.3 is magnesium, and that's the fourth and final mark on this question. Looking at question 7, this is an acids question. It's quite late on in the paper, so it's quite a difficult acids question in places. However, as with most questions, there are one or two things that everybody can attempt, and then you're going to build it from there. Okay? Now, bad thing about this question is that A is actually quite difficult, so it can put a lot of people off, but again, I'm going to encourage you to stick with the question and pick out the things that you can do. So, let's start off by looking at A. So, calcium hydrogen sulfate can be made, so let's put that on the right hand side of this equation, because part A is asking us to write an equation for the formation of this, and we make that by reacting an excess of sulfur dioxide gas with calcium carbonate in water. Okay, I'm going to put the water there. Sometimes you'll get these questions and they talk about being an aqueous solution, but the water's not actually important. So we'll leave it there and see if we need it. Okay, so first things first, if we look on this side, we can see that we've got 2 sulfurs. I've put a 3 there and it needs to be a 2. Okay, so we can see that we've got 2 sulfurs on this side. That means that we're going to need 2 over on this side. And then we're going to look at the calcium carbonate. So the calcium is there on the right hand side, but the carbon is not. So you've got to think about what else might be made in this reaction. If you think about carbonates, it's very likely that we're going to get CO2. Okay, so this equation, quite a lot of it is educated guesswork. And again, I've spoken to you a few times about this, that you might get these equations and they're really kind of there to slow you down, to stretch the people who are going to have a go at it. But really what you've got to be thinking about is timing, because following this question you've got some nice easier acid stuff to do, and then you've got a big transition metal question at the back of this paper, and if you spend 10 minutes working out this equation for 1 mark, you are going to seriously run short on time. Okay, so if you get stuck on this type of question, leave it and come back to it if you've got time at the end. Okay, because you've got to weigh up the benefits of getting this 1 mark versus getting on to the rest of this question and the final question on transition elements. However, this is our balanced equation that we'd end up with, and now we're going to carry on. Okay, so as I said, first bit of this question is quite horrible, but the next bit's not so bad. So what is meant by a weak acid? Okay, so all you need to say there, as we've done many times in the past, is say that it partially dissociates in solution. And then we've got to write an equation for the dissociation. So here is calcium hydrogen sulfate, and that's going to behave as an acid in solution. So if we look at it, we know that the metal ions don't play any part in kind of acidic action or buffering action, so we can get rid of that. So we're going to have HSO3. Okay, and it's going to have a minus charge because remember calcium is in group 2. There's 2 HSO3s, so each one must be -1. It's a dissociation equation, so we have to have reversible arrows. Okay, you won't get that second mark if you put a normal arrow in here. If it's dissociating, it's going to lose a proton, so there's the H+. And we're going to have SO3, and it's going to be 2-, and there are 2 marks. Next bit, again, this bit's quite tough again. So we've got aqueous solution of calcium hydrogen sulfate oxidizes magnesium. So there's the calcium hydrogen sulfate, and it's going to react with some magnesium. Now we know that on the right hand side we're going to get hydrogen gas because it tells us that. Magnesium is in a zero oxidation state here because it's an element, and it's going to go to +2 on this side because it's being oxidized, and it's in group 2, so that's its only option, is to be +2. So let's look over here at what we can match that all with. So we've got rid of the hydrogens and we're left with some SO3 ions. So we can make MgSO3 because of course SO3 is 2-, we've just seen that up here. Mg is 2+, so that's a perfectly good answer. Now we're going to deal with the calcium. Again, calcium's in group 2. We've got a couple of these SO3s knocking around, so we're going to make that in solution as well. And that's going to be our equation. For the ionic equation, I'm now going to do a little bit of work on the side here. So calcium hydrogen sulfate in solution will actually exist as Ca2+ and 2 lots of HSO3-. Magnesium's a solid, so that just stays as magnesium. Okay, so this is writing ionic equations now. On the product side, we've got H2, which is a gas, that stays as it is. Magnesium sulfite will end up as Mg2+ and SO3 2- in solution, and similarly that calcium compound will split into ions 2. Okay, so now we're going to do our cancelling. So on the left I've got Ca2+, and on the right I've got Ca2+, that can disappear. And then there's nothing else, so on the reactant side I'm left with these two things, so let's put that in there. 2HSO3-. The magnesium stays as it is because that was a solid. And on the right we've got H2 and Mg2+, and 2 lots of SO3 2-, and that's our ionic equation. Bottom bit, again this is quite a nice question. So we've got HSO3- acting as either a Bronsted acid or a Bronsted base. So we've got an acid is a proton donor. Okay, so we should get a mark for saying that because it's out of 4 marks. So let's show HSO3- donating a proton, so it's going to become H+ and SO3 2-. So a lot of this is quite repetitive in this question. And a base is a proton acceptor. Okay, so we've got 1 for that definition, 1 for this equation, 1 for this definition, and then when we write this equation we're going to get that final mark. So we've got HSO3-. This time it's going to gain a proton, so it's going to become H2SO3, and that minus has gone away because it's gained an H+. So that's the 4 marks in part 3. Here in part C, we're talking about a weak acid because we're talking about a carboxylic acid being used as a food additive. We've got a Ka value, which again reinforces the fact that it's a weak acid, and then it's telling us that this acid is analysed. Okay, so if we think about, again, I like to draw pictures of what's going on when I'm answering a question. So I've got a volumetric flask in my mind like this, which is 1 decimeter or 1000 centimeters cubed, and I'm dissolving 0.7369 grams of HA in there. And the pH is 3.52. So let's look at this question in terms of what we can do. Now I always say to you, if you see a mass, turn it into moles. Now that is impossible with this question because we don't know the MR of HA, so we can't do N equals M over MR. Okay, but what we can do is if we carry on, we've still got those kind of mark grabbing techniques because we've got a pH down here. Okay, and you should remember that if you can see a pH, then you should turn it into H+ concentration. So that's exactly what I'm going to do now. So the concentration of H+ ions, we do 10 to the minus pH, so 10 to the minus 3.52, and that gives us a concentration of 3.02 times 10 to the minus 4 moles per decimeter of H+. Okay, so again, if you see a pH, turn it into H+ concentration, because you'll get 1 mark for doing so. Worthwhile pointing out at this point, this is an unstructured moles calculation, so you've been given quite a bit of text and then a big space to do your working in. Examiners really don't like it when there's random calculations and numbers all over the place, so please do label exactly what it is that you're doing at each step, just to make it very clear to the examiner. It's very easy for them to find the marks and award you the marks as well, kind of ensuring that none of them get missed. So, carrying on from there, we've got the concentration of H+ ions. We know that we're dealing with a weak acid because we've been talking about that earlier in this question. So we're going to look at writing a Ka expression, okay? Because it's not a buffer, we've not mentioned buffers, we've not mentioned neutralization, so we're just going to deal with the Ka expression. And because it's a weak acid, we know that H+ is equal to A-, and we can use the squared version of this like that. So we're going to get a mark for writing out which equation we're going to do, and then we need to substitute in, or we need to rearrange, and then we need to substitute in, because if we're thinking about what we've got Ka given to us in the question, and we've got H+ because we've just worked that out. So what we're working at is the concentration of Ha, and that's going to be equal to H+ squared divided by the Ka value. So again, substituting those numbers, 3.02 times 10 to the minus 4 is our H+ concentration, and the Ka value is up here, so 1.51 times 10 to the minus 5. And quite generously, I thought, you get a mark for just substituting in those numbers. You equally will get a mark for being able to use your calculator to come to an answer for that. So that's another mark for us. So we're on 4 so far. And then if we've got a concentration, now this bit takes a little bit of thinking. So if we've got 6.04 times 10 to the minus 3 moles per decimeter, so this is moles per decimeter, that means we've got 6.04 times 10 to the minus 3 moles in 1000 centimeters cubed, and then I want to turn that into an MR. Okay, so although I've got moles per decimeter, that means I've got that many moles in 1000 centimeters. Look at the question. That says I've got 0.7369 grams in 1 decimeter, or 1000 centimeters cubed. So I've got M, and I've got number of moles, and I've got M. If I want to do MR, I do M over N. Gives me 0.7369 divided by 6.04 times 10 to the minus 3, and that gives me an MR of 122, and that is mark number 5. Okay, so one more to get. So we've got the molar mass of HA, so let's put that in there. And then it says possible formula for the carboxylic acid. So if you think about that carboxylic acid, let's just change the colour so that we see this is that final mark. The carboxylic acid has some kind of alkyl chain, and then it's got the Cu group on the end. And the Cu group adds up to 45. Okay, the total for this compound is 122. So if we take away the Cu group, then what we're left with is 77. So what I now need to work out is how many C's and H's make up 77. The fast way of doing this is to just do 77 divided by 12, and I get an answer of 6.41. So the chances are I'm going to have 6 carbons. Okay, and then if I put the hydrogens around that, going to take me a while. And then I'm going to check by adding that up. So 6 lots of 12, and then I've got 13 hydrogens. If I add that all together, I get 85, so that's too much. So what I need to take away from that, if that adds up to 84, I need to lose 5. The easy way of losing 5 is to think about taking some hydrogens away. I know this structure doesn't make sense, but bear with me for a minute. Okay, so I'm getting rid of 5 hydrogens, and I'm left with C6H, 1, 2, 3, 4, 5, 6, 7, 8. Has that brought me down to what I need? I'm not sure it has actually. So 6 times 12 plus 8 gives me 80. I've still got too many hydrogens, so I'm going to need to get rid of another 3. So 8 take away 3, that's 5. So C6H5 is the R bit of this, because that adds up to 77. And you can see really that all that is trial and error. So it takes a few minutes, but we got there in the end. So the formula of this compound is C6H5, and then there's the Q group on the end. Now the Marx scheme allows you to write this in a couple of ways. So you can write C6H5 and that, which makes sense actually, because if you think about your knowledge of F324, which should be building up by now, then that would be benzoic acid, wouldn't it? Okay, so this is a compound that makes sense. If you wanted to just write the molecular formula, then you could get away with that as well, which would be C7H6O2. Either of them is fine for that final mark. Okay, so again, reasonably straightforward acids calculation. Just make sure that you make it clear what you're doing at each stage by labelling the various things that you're doing. Carrying on down to the bottom, so the last bit of this question. Considered analysing the solution by carrying out a titration with an alkaline solution of known concentration. They decided not to do that because HA is a weak acid, so only a little bit of the H plus ions would be neutralised. And then you're going to suggest whether this person was correct in rejecting the titration method. So once you've read this through a couple of times, think about what this person is suggesting. What they're suggesting is that when you neutralise HA, let's put that into black pen, so you're taking HA, okay, they're suggesting that because it's a weak acid we only get a little bit of H+, and they're suggesting that as soon as you add some sodium hydroxide that's going to be gone and there will be no more. Okay, so the answer is that they are incorrect, and the reason is that more acid will dissociate. Okay, so we talked about this little in class. I can't spell. If you take away the H plus ions by neutralising them, then this equilibrium will shift to the right to restore the concentration of H plus ions, and it will carry on doing that until all of the acid is gone. So in just the same way as if you started off with 1 mole of this, then 1 mole of it would react in the same way as if you add 1 mole of HCl. 1 mole of HCl would react. It'd just do it faster because these protons are already dissociated, whereas in the weak acid we've got to wait for it to dissociate and then neutralise as well. So this person is incorrect because more acid will dissociate and it's got the same number of moles as you would expect, so that titration is a valid method. In question 8, we're looking at transition metals. The question is about vanadium. Now remember, vanadium is not specifically referred to on the specification, so you're not expected to learn the colours of any of these ions, but you are expected to be able to work your way through this transition metal question. Part A is asking for an electron configuration, so regardless of how you feel about transition metals, you should all be able to do the electron configuration, because what this is really looking at is whether you can get your periodic table and find the atomic number of vanadium. So if you were to do that, you would find that vanadium is number 23. And if we were going to write an electron configuration for that, it would look like this. That's 10, that's 12, that's 18, that's 20, and that's 23. Okay, so that's our vanadium atom. However, the question is not asking for the vanadium atom, it's asking for it in a +3 oxidation state. So what we're going to do is get rid of 3 electrons. Now remember, the 4s electrons go first, followed by the 3d. So what we should be left with, following on from what's there, 3s2, 3p6, the 4s2 have gone, and we've lost 1 from the 3d. So that is what we should be left with to get the mark in this question. Next it says, suggest why vanadium does not form ions in which the vanadium has an oxidation state greater than +5. So if you think about the kind of outer or valence electrons, they are these ones. So all we're going to say here is there are only 5 electrons in the 4s and 3d orbitals. Okay, so if you think about a transition metal, it's the 4s and the 3d that are going to be the ones that they lose when they're going through the various oxidation states, and for vanadium we've only got 5 electrons there available to do that, so it can't lose more than 5 electrons, essentially is what we're saying. Carrying on to the bottom of this question, so this is where this question really starts to get difficult. Now, if you've been looking at past F325 papers, you'll notice that there is a tendency towards these questions where we've got a number of stages or steps, and they're quite difficult to follow all the way through. So what you've got to do is train yourself into reading these questions and really kind of annotating them as you go, so that when you come to answer what OCR are asking for, you've got some sort of idea already built up. So if we look at this, we've got vanadium metal reacts with acid to form a yellow solution and made up to 50 centimeters cubed in a volumetric flask. So personally, I like to draw pictures of what's going on, because that tends to help me. So I know in my volumetric flask I've got 0.126 grams of vanadium and the volume is 50 centimeters cubed. Okay, that's going to help me later on. Next it says this has got VO3 minus ions in it. Okay, so read that again. 0.126 grams of vanadium is dissolved in this 50 centimeters cubed in a volumetric flask, and it contains VO3 minus ions, which are in a +5 state. Okay, so I'm going to come back to that later. Next, the yellow solution is reduced to form a violet solution containing Vn+. So in this stage I've got VO3 minus turning into Vn+. Okay? And I'm going to do that to the whole 50 centimeters cubed. Next, I'm going to take 10 centimeters cubed of this and put it into a conical flask and titrate it with manganate. Okay, so that's what's happening. I'll run through my picture again. It might help you to get used to doing this, and it might not. Try it and see. So I've got 0.126 grams of vanadium dissolved in this 50 centimeters cubed volumetric flask. Then I'm going to turn the VO3 minus into Vn+, and I'm going to take 10 centimeters cubed of that solution and titrate it with potassium permanganate. Okay, and then I might also actually write on here at the same time whilst I'm at it, the concentration of the permanganate is 0.0225 and the volume of the titer is 13.2 centimeters cubed. Okay, and that's going to help me later. So now I'm going to look at answering this question. So we've got, why is there no clear colour change at the end point of this titration? So if what you think about is, in this 10 centimeters cubed, and read it here, it says 10 centimeters cubed of the violet solution. So in this conical flask, we've got a violet solution. Let's just write that down here. Is violet. Okay, so we've got a violet solution, and to that we're adding potassium permanganate. You should all know by now that the colour of manganate ions is purple. So we're adding a purple liquid to a violet solution. So that's definitely not going to be a clear endpoint. So we've got Vn plus is violet and KMnO4 potassium permanganate is purple. Don't need to say any more than that because that's fairly clear. Violet to purple is not going to be a clear colour change. Okay, so that's C part 1 over with, and C part 2 is where it gets really difficult. So if we just take a quick look at C part 2, and it says determine the value of N in the Vn plus ions formed in stage 2, and then construct an equation for the reaction that takes place during the titration. Okay, so it's going to be a little bit of skipping backwards and forwards between the two pages. It's not very well set out for me, but we're going to work our way through it. So if we go back to what we had in this question, so we'll go back to this picture that we had and work our way through it. So the first thing we see, and again this comes down to kind of, if you look at this and you're totally confused by it and you don't know where to start, you can't afford to drop the easy mark. So if you're looking at this, things that should really stand out to you, we've got a mass, 0.126 grams of vanadium. Well, that's straightforward enough to convert into moles. So, and again, if you've drawn it out like a picture, you'll see that 0.126 grams, and you should be thinking, right, if you see grams, turn it into moles. So let's go and put that into our answer on this page. Okay, so we're going to do moles of vanadium, and that's in 50 centimeters cubed. Okay, so very, very important. Examiners' reports quite often comment on the fact that when you get a question like this where there's either a lot of lines or a lot of space, and you're expected to do an unstructured moles calculation, which is what this is, that people tend to write at random all over the place bits of calculations, and it's very unclear what number is what. So what I want you all to get used to doing is labelling what you're doing. Okay, so I've just said we're going to work out the moles of vanadium in that 50 centimeters cubed. Label what you're doing and make it very clear for the examiner. And what we're going to do for that is, not CV, N equals M over MR. Okay, because we've got a mass, which was 0.126 grams. MR of vanadium, periodic table, you'll find that it's 50.9. Okay, and that gives us the number of moles of vanadium as 0.00248. That's going to be our first mark. So, as I've said to you, if you see a mass, turn it into moles because you're going to get a mark for it. Okay, you can't afford to be dropping marks. Simple marks like that, should be picking them up. Carrying on, so let's look back at that picture again of what we were doing. So we've dealt with the number of moles. Let's give ourselves a tick for that. And we said that's in 50 centimeters cubed. Okay, next thing I'm going to think about is in my titration, so I'm going to follow this picture down. In my titration, I didn't use all 50, I only used 10. Okay, so if I know the number of moles of vanadium in 50 centimeters cubed, then I want to know how many is in 10 because that's what I actually used. Okay, so let's go back to the answer because we need to set it out really nicely for the examiner. So we're now going to do moles of vanadium in 10 centimeters cubed because that was the amount that we titrated. Okay, so if we know the moles in 50, to get to 10 we're going to divide by 5, and that gives us okay. So again, relatively straightforward because all we're doing is looking at that dilution, that division factor. And if we've drawn that picture or we've got a mental picture of what's going on, then it should be fairly straightforward to 1, work out the moles, and 2, kind of divide that down to being 10 centimeters cubed. And already we've got 2 out of 7 marks. Look back again. So we can tick off the fact that we've dealt with the fact that it's in 10 centimetres cubed. And now we're going to come over to the manganate, because again, if you get into the end of the paper, you're a little bit short on time, or you've got to this question and you don't quite know what to do, then what should stand out to you is that we've got a concentration and a volume of manganate. So again, you're thinking AS moles calculation. So let's go and put that into our answer. So we should have moles of MnO4 minus. Okay, so again, you can see that I'm labelling what I'm doing in each step to make it very clear to the examiner that I know what I'm doing. So for that, we're going to use CV over 1000. Okay, on the previous page we saw that the concentration was in the question, the final titer volume was in the question, and all we're doing is putting them into our AS calculation, and that gives us the number of moles as being 0.000297. Again, very straightforward moles calculation, 3 out of 7 marks so far. So whenever you get to these difficult calculations on your F325 paper, then what you need to do is look for the easy things to do. So masses into moles, concentrations and volumes into moles. Do those conversions and you're going to pick up some marks. Okay, after this is where it gets slightly tougher. So what it said in that question is that during the titration, you've got this half equation, because this is given to you on the previous page. Okay, so all I'm doing is copying that across so that I've got it in front of me here. And it also says that the Vn plus ions are turned back into VO3 minus ions. So they are the two half equations. Now we know that there's going to be some electrons in this second half equation, but we don't know how many, and that's what we're dealing with now. Okay, so if I look at writing an equation that goes with this, because what I'm going to do essentially is add these two things together. So I've got MnO4 minus plus Vn plus and that's going to turn into Mn2 plus and VO3 minus. Okay, I'm going to worry about the H pluses and the waters later, because for the minute all I'm concerned about is the manganate and the vanadium reacting. Okay, now to kind of for ease and for clarity, I'm going to write my numbers underneath, so I know that when I do this titration, it's this many moles of manganate reacting with this many moles of Vn plus. Okay, so the next thing I want to work out is what is the stoichiometric ratio. What are the big numbers that go in front of these two things in the equation? So for that, I'm going to find the ratio between these two numbers, and what I find is that it's 1 to 1.67. Now, you should all know that in chemical equations we don't have decimals, so I can't put 1 MnO4 and 1.67 Vn plus. That doesn't work. So I need to multiply this fraction out, and what I'm going to do to do that is if I times it by 3, then I get a ratio of 3 to 5. Okay? If in my working out somewhere I've shown this 3 to 5 ratio, then I'll get a mark for it. Next thing I'm going to do is put those numbers into this equation that I'm coming up with. So 3 MnO4 reacts with 5 Vn plus, and that's going to make 3 Mn2 plus and 5 VO3 minus. Okay, so already we're starting to build up this equation. Next I'm going to look at what is N, okay, because if we look at those bullet points, we've got to determine the value of N. So let's go back down to that equation again. Now we know that if we are reacting manganate, then what's happening to the manganate is we're going from +7 to +2, okay? And there is a change of 5 electrons per Mn, okay? You can see that because we're going from +5 to +2, or you could even look in this equation and say, okay, well each Mn changes by 5 electrons. Okay, we've got 3 Mns, each one's changing by 5, that's a total change of 15 electrons in that equation for the manganese. Okay? It's a balanced redox reaction, so that means that the vanadium has also got to change by the same number. Okay, so if 3 manganese atoms gave us a change of 15 electrons, then the 5 vanadiums have to give us a net change of 15 electrons too. Otherwise this equation wouldn't be balanced. Okay, so we've got 15 electrons being changed by 5 vanadiums, which means that each vanadium changes by 3 electrons. Okay, so this is the tough bit to follow, so let's just go through it again. Each Mn changes by 5 electrons, going from +7 to +2. There are 3 Mn's in this equation, so if each one changes by 5, that's 3 times 5 gives us a net change of electrons of 15. Because it's a balanced equation, we've got to have the vanadium changing by 15 as well. Okay, so 15 electrons, but we've got 5 vanadiums, so 15 divided by 5 means that each vanadium changes by 3 electrons. So we know that, let's just put this back up here, the vanadium here going to here is changing by 3 electrons. So let's just write on top of this. We said that vanadium in VO3- is +5. Okay? We know that vanadium's being oxidized because the manganese is being reduced. It's going from +7 to +2. We know that vanadium's changing by 3. So +5 take 3 is +2. And that's the charge on the vanadium. Okay, it's taken a while to get there, but that is our answer. So N equals 2, and we get a mark for that. So we've got 5 marks so far. We've got the 3 moles calculations at the top, we've got the 3:5 ratio, we've got that quite tough step of working out that N is 2. Okay, last little bit then, to look up at those bullet points again. We determined the value of N, and then it says construct an equation for the reaction that takes place. Well, we're nearly there, so we're going to look at this equation here. And all we need to do now is balance it. So on this side we've got 12 oxygens, on this side we've got 15 oxygens. So we're going to need to add some water to this side. So we're going to add 3 H2O plus that. And then on this side we're going to need to deal with the hydrogens. So on this side we're going to have 6 H+. Your final check should be on the charges. So let's put that N as a 2, because we just worked that out. 5 times 2 is 10 plus. Take away 3 minuses, that's +7 on the left hand side. On this side, 6 pluses, that's 12 plus in total. Take 5 minuses, that's +7. So both sides are balanced in terms of charge, so this is the correct equation. And for that we get 2 marks. It's 1 for your species and 1 for your balancing. And that's our 7 for this final question. So if you just try and scroll that back up a little bit, and hopefully you'll be able to see what was going on. Obviously I've just missed those moles off at the top, but hopefully that's taken you through question 8, which is a very, very difficult question on this paper. But again, just going back and reiterating the things that you can always do. You can always look at these moles calculations and do the easy things, even if you can't get as far as this ratio at the end.